by Oscar Velasco Fuentes, and he's going to be telling us about stirring vortices with vorticity holes.
Okay, thank you. Let's start with this simulation. It is not actually the exact topic I'm going to talk about today, but it is an ICER movie, and also is related. Well, I'm going to show you the simulation of the motion of an inviscid homogeneous fluid in 2D. It is computed with contour dynamics. The initial condition is the following. I have vorticity which equals 0 in all the black regions, and then vorticity which is uniform in regions of uniform color. Highest is this yellow region, and you can think of this being vorticity 4, and then 3, 2, 1, and 0. And this would be something like a ranking vortex, except that we can observe that there are 2 holes of vorticity, and we have also the same steps 0, 1, 2, 3 to 4. Now let's see what happens in this situation. Okay. Well, it was so quick that what we see is that these 2 initial holes are they merge into a single hole in a very short time, and in the process of merging, they eject filaments of non-vortical fluid, just like in the case of the merging of normal vortices. We also see that there are some perturbations in the boundary of the vortex. So this problem is a little bit more complicated than the merger of fluids because of this interaction between the holes and the boundary. Well, today I'm not going to talk about this process of merger, but about something that looks a little bit boring if one looks only to the boundaries of the vortex and the holes, because they are not filamented, and they undergo only small perturbations, change of shape. I'm going to show only one example. I have collected several examples in oceanography and atmospheric sciences, but I'm going to show you this example of a vortex hole in a magnetized electron plasma. What we have here is the electron density. This is the initial condition, and there is a bump in the density of electrons marked by this darker dot in this position. We know that the electron density can be interpreted as the vorticity, and so we have a similar situation, a ranking vortex with, in this case, instead of a hole, a bump. But this bump perturbates the boundary. This boundary, the wave that is generated on the boundary breaks, and then it closes again, and it brings into the vortex a hole of vorticity. So now a hole of vorticity, yes. And so now we have inside this ranking vortex a pair of bump and hole of vorticity that behave like a vortex pair in a regular fluid. Well, let's see very briefly the motion of the vortex and the holes, and start with the definition of our problem. As I mentioned already, we have a circular region of uniform vorticity, and in this circular region of uniform vorticity, I'm going to have 2 kinds of holes. The first one is going to be an elliptic concentric hole, And in this problem, I have 3 parameters. I have the size of the hole given by the major semi-axis divided by the radius of the vortex and the aspect ratio of the hole itself. Of course, there is a third parameter here, which is the depth of the hole. Today, I'm going to talk only about holes that have 0 vorticity, but you can have also different smaller larger than 0, but smaller than the vorticity here, which is assumed to be positive. In the second problem, I'm going to have the same circular Rankine vortex, and I'm going to have two circular holes which are identical, and vortices or holes that have the middle point coinciding with the center of the Rankine vortex. So again, I have only 2 parameters, which is the size of the holes and the separation of the holes. The hole depth I'm going to consider as being -1 in this definition during this talk. As I said before, the evolution is rather boring. We have here the time going from left to right and from up to bottom, and it is given in eddy turnover times of the original Rankine vortex. And we see that the hole, the elliptic hole, simply rotates in the sense given by the Rankine vortex, and we see small deformations. You can see very clearly that it is a more elongated vortex than this original one. Let me say that this is the only elliptic situation, and I mean, in the initial time is the only time when the outer boundary is circular and the inner boundary is elliptic. All other times there are small perturbations, and they are not exactly circular and not exactly elliptical. It is difficult to see the formation on the boundary, and that gives you the measure of the small perturbation that this hole is provoking, even though the hole is rather large. Well, all vortices in this region, this is the parameter space. I have the size of the vortex here, and I have the aspect ratio in this axis, and the behavior I show is the characteristic behavior in all this region. In this region, the vortices are unstable. In this area, it is the hole that it is filamented, and in this region, it is the outer boundary that forms filaments. And it is reasonably well predicted by this Lob's criterion for the stability of the Kirchhoff vortex. This is very well known, and this is a separatics criterion that is going to become clearer in a couple of minutes. What happened with the pair of holes? In the initial conditions, I have a circular outer boundary and 2 circular inner boundaries. As time goes on, we see that the holes rotate in the sense given by the original Rankine vortex, and they undergo also small perturbations. Again, it is difficult to appreciate any deformation of the outer boundary. That means that the perturbation is small. It is easier to see that the holes are being perturbed. And again, I have here the parameter space, the size of the vortex in this axis, and the separation of the holes in this axis. Now I have these 2 curves, again the separatics criterion and the critical distance for vortex filamentation. I'm not using the critical distance for merger, which is a little bit lower over here. It's about 3.3, as it is well known, because I'm interested only in the initial conditions that do not produce any filamentation either of the holes or of the outer boundary. And it is in this region of the parameter space that we observe the behavior that was shown in the previous slide. So the thing seems rather boring if we only look at that at the motion of these boundaries. But what happens if we look at the motion of the particles, particularly inside the vortices. Let me show another animation very quickly. Oh, it's already moving. Very quickly. This is obviously the boundary of the ranking vortex, and this is the boundary of the hole. And I have drawn a large number of particles with trails proportional to the speed of the particles. And this is what we observe as a vortex and the hole evolve, how the motion is produced within the hole and in the vortex. Okay, I think this is enough. Well, the best way to analyze the motion of the particles, it is using a frame that rotates with the holes. The reason is because in this frame, this particular frame is the frame where the vortex and the hole are the closest to being steady solutions. So in this frame, we don't observe anything but the small deviations from the circular shape of this boundary and the small deviations of this boundary from the elliptic shape. So we would see only the pulsations. So this axis growing and becoming smaller, and this doing exactly the same. And the smaller the perturbation, of course, the smaller the variation of the velocity field from this picture that I'm showing here. The important thing in these pictures is that we observe hyperbolic points inside the vortices and also hyperbolic points outside the vortex. But it is important to notice that the strongest deformation occurs inside the vortex, just outside the vorticity hole. That means that the regions of intense stirring must exist inside the vortex, and we can prove this by applying ideas from dynamical system theory. And the first or one of the things that one can do is compute the stable and unstable manifolds of these hyperbolic points. And one of the methods I use is the finite time Lyapunov exponents developed by Haller in 2001. And in this method, I first define a grid of initial conditions in some region of the flow. This is actually the boundary or the border of the hole, and the boundary of the vortex would be somewhere over here. I compute the trajectories of all the points in this region up to some time t, and then I find the largest finite time Lyapunov exponent or this field by this expression. Sorry for the this occurred during the translation from Microsoft to Apple, but the important thing is that the reaches of this scalar field are the finite time invariant manifolds. So all the reaches in this area are the in this case stable manifold of the hyperbolic point. If we see this structure for 4 different initial conditions, these are 2 initial conditions with the same size. This is a smaller hole, but different aspect ratios. So very elliptic one, a more circular one, and we have here the same thing, but with larger holes, so large that we can observe the boundaries of the vortex over here, which we cannot do in this case. We see that they are very similar, the two structures, and so we see that the manifolds are very close to the separatrices of the unperturbed velocity field. What happens with the steering? Of course, this is not a periodic flow, so we cannot apply these techniques of for Poincaré maps, for example, or we cannot use the CAM theorem or anything like that. But we see that there are analogs to this of these elements in this picture. As a matter of fact, the boundary of the vortex and the boundary of the hole are invariant curves which trap particles permanently. So they are CAM-like curves, but they are of course not the only ones. We can see that larger than this CAM-like curve, there are these other red CAM-like curves, and smaller than this larger CAM-like curve, there are these blue ones. And in between, we see that there is a region of chaotic behavior. Also, we can see that there must be some CAM-like curves in these areas. A very similar. How long do I? Okay. A very similar thing happens with the pair of holes. Again, the largest deformation occurs exactly, well, in this case, it is exactly in the center of the vortex. So this is the hyperbolic point that has the highest probability of surviving any perturbation, and so this is the region where there is the highest probability of having intense steering. As a matter of fact, this survives. These ones do not survive, so we don't have intense steering outside the vortex, only inside. In this case, I computed the manifolds using a different technique. This is just to show you the manifolds, the unstable manifold in red, the blue manifold in the blue manifold being the red is unstable, the blue is the stable, and we see this transverse crossings indicating that there is chaotic region, chaotic motion of particles in the center of the vortex in this area. Again, the steering inside the vortex for two different initial conditions, and we see the same features. This the boundary of the vortex is a CAM-like curve. So are the boundaries of the holes. We have other CAM-like curves here and intense steering in the middle. Let me finish with some conclusions. The most important one is, of course, that the strongest steering occurs in regions of highest vorticity, so within the vortex. The elliptic hole steers an area that grows with the increasing hole size, which is something that we could expect, but rather unexpected, also grows with the aspect ratio. So more circular holes produce strongest steering. In the other case of the circular holes, a pair of holes, they steer an area that grows again with increasing hole size, something we expected, but decrease with the separation. And that is simply because the perturbation also decreases with the separation. Thank you.
We'll start front, go to back. So, Conrad first.
If you consider this in a rotating frame,
Yes.
is, for example, the case of a single elliptical hole.
Yes.
In the rotating frame, that would be an elliptical vortex in a big hole, rather than a hole in a big vortex.
Yes.
In which case, it will be like the Kida vortex. with a slight modification that it interacts
Yes,
the
that-
boundary with the
exactly.
distant boundary of the hole.
That's exactly the
There's a lot
case.
of work done on stirring the Kida vortex, except yours is perturbed in a very particular way by this weak interaction
Exactly.
rather than
Yes.
randomly.
Yes, that's right.
May I please give a few words supplement to the talk? In our laboratory has performed experiments, transportation of dye from a spot put on the surface of generalized Röntgen vortex. Generalized that it's not only rotate but also the circulation. And the round spot in the center of the vortex is transformed into spiral arms, like in the picture which you can see. But orientation of arms in opposite direction of general rotation. Published in Russian Journal of Mechanics. A question.
Was that a question?
Sorry?
I didn't understand the question.
I show you.
Okay. Yes, okay. Let me just comment on the previous comment. You're right, there is a lot of work on the Kida vortex. Remember, but the Kida vortex is always elliptical. And in this case, the vortex is not, the hole is not elliptical, except in the initial condition. After that, it loses the elliptical shape. And for medium to large holes, these deviations are substantial. Yes. Yes, it's very similar, but it is not elliptical except at the initial time.
Okay, thank you. I believe now it's time to break.